Hello and welcome to Statics. In this video, we're going to be introducing friction. In a lot of cases, friction can be used by engineers in order to help provide support in their designs, but friction is different from the other types of supports we've studied this semester because it's limited. Once a force to overcome friction becomes large enough, motion can occur. So we have to be really careful with how we address friction and make sure that the conditions are right to be able to count on it as a support force. So let's go ahead and get started. So the purpose of this presentation is just to introduce friction. We'll talk about what friction is and how it works, and then we'll move on to discuss how friction can provide support with systems in equilibrium under certain conditions. So our first learning objective here is to just basically define what friction is. We'll talk about two different types of friction, static friction and kinetic friction. And then we're also going to look at friction through a typical friction graph because it can help us understand what these topics are a little bit deeper. So first things first, how is friction used in a statics analysis? To me, the first thing that comes to mind here is a typical ladder. When we use a ladder in order to hang holiday lights or to change a light bulb or to work on our houses, anything like that, we have to rely on friction in order to not get injured. So if we have a typical ladder like this is shown here, the ladder is shown between points A and B, we're going to have a certain amount of friction available at point A and a certain amount available at point B as well. And if the circumstances become right, then the ladder might move under us and then we're at risk of being injured. So we need to understand how friction works as a support force on top of the normal forces that are available here. So we will have a normal force here at point A and a normal force here at point B, and those do also help help our ladder from moving, right? It's not going to fall through the ground. It's not going to fall through the wall, but there's nothing here right now that's going to support our ladder from sliding down the wall and causing us to fall. So that's the point at which we're going to depend on friction in order to help us out and make sure that we stay safe. So the first thing I want to talk about before we look at how friction's used in statics is I just want to talk about a typical graph that we would see in friction. So a graph like this would be basically created through experiments so that we can understand how friction would work under certain conditions. And if you conduct enough experiments, you start to see a similar pattern. And what that pattern is that if we look at how much friction force is available and plot that friction force on the vertical axis, and then the force P, that's the applied load, that's how much force is trying to cause our object to move. So that's the applied load that is applied to an object, and then how much friction force is a result of the situation. And basically what we do is we split this graph into three different sections that are worth talking about. When I think about friction, I like to think about just a nice box resting on a steady horizontal surface, right? And if I walk up to that box and I start to push it, the box is going to resist me because of that friction force. And it will continue to resist me as I increase how much force I apply until finally it moves, right? So at the beginning, there is no motion around my box. It's just sitting there resisting me pushing on it. But if I apply enough force on this horizontal axis, eventually the box is going to start to move. Well, what ends up happening here when we run this experiment over and over again is that we notice some trends that end up showing up. And what the trends are is that when we're in no motion, that means that our box is in equilibrium. And we know from our study of equilibrium all semester, that means all of the forces have to balance each other out. So if I walk up to my box and I push it with 5 pounds, if 5 pounds is trying to move my box, say to the right, then the friction force is going to be equal and opposite to that. So that means that the friction force is also going to be 5 pounds. So I have 5 pounds of applied force, 5 pounds of friction force available to me. Let's say I add another pound, I'm now 6 pounds. The box is going to resist me with 6 pounds. 7 pounds of applied force, the box is going to resist me for 7 pounds. And that's going to continue where my applied force and my friction force are going to be equal and opposite to each other. That's going to continue up until I get to this point at the top, which we'll talk about in a minute. It's called the breakaway point. But down here under this case here, my box is in equilibrium, and my applied force and the friction force present are equal and opposite to each other. So if I were to measure the slope of this line, the slope of this line would be 1, because we've got the same change in y as we have change in x due to our applied load versus our friction force available. So always in this entire area here, we've got enough friction to prevent motion. So if we want to use friction as a support force in engineering, we really are targeting to be able to stay in this area right here. Now, what ends up happening here is I continue to increase my applied force. That amount of friction force is also going to increase. And then when I get right here at this point, notice that this point is the transition between having no motion and having motion. So this is what we call the breakaway point. And the breakaway point is literally that. It's the point at which my box breaks free and it finally starts to move, because now I have overcome the amount of friction present. So if I've got this first stage here where my friction force is equal and opposite to my applied force, right here, this is where I enter stage 2. A lot of students taking physics learn that this is the point where we have a static friction equation, where the static friction is equal to a coefficient of friction. So this coefficient of friction is the Greek letter mu. I look at it and I see the letter P where the top of it has been erased off. And this is the coefficient of static friction. You multiply that by how much normal force is present, and the two combined is going to tell you how much static friction force is available. But here's the thing. A lot of students mistakenly understand when this equation applies. Remember what we talked about stage 1. In this area here, there is no motion. My box is static, as in not moving. But all the way up until this point here, how much friction is present is equal and opposite to the applied load. So I've got my friction force and my applied load being the same down here under stage 1, and it is only at this peak here, this breakaway point, that this equation applies. And then after that, we enter in what's called stage 3. We've got our box moving now, and if I continue to increase how much force I'm applying to my box, then my box is just going to start to accelerate. It's going to start to move faster and faster. But under that accelerated motion there, I still have friction. Friction's still resisting me. I can feel it in my hands as I'm pushing on my box. But in this case here, we've entered into stage 3. In stage 3, we talk about what's called kinetic friction. That's the friction that we observe under motion. And for kinetic friction, that force is going to be equal to the coefficient of static friction, mu sub k, and then that's going to be applied to the, or multiplied by the amount of normal force that's present. So a typical friction graph, something that I want you to be familiar with. In stage 1, there's no motion. Our friction force is equal to whatever applied force we have. It's in stage 1, that's when we have equilibrium. At stage 2, we're on that teetering edge. If I add even a tiny bit more force, my box is going to start to move. It's only at this breakaway, this peak point here, where my static friction equation applies. And then in stage 3 here, that's this flat region right here, this is where my box is going to move. And it's going to move under opposing force of kinetic friction equal to mu sub k times the normal force. Okay, so that's a little bit about what friction is. The next thing we're going to do is we're going to take a look at a rigid body in equilibrium, and we're going to talk about what that equilibrium looks like when it comes to friction. When we talk about friction in this chapter, we're going to only talk about dry friction, which means that there's no lubrication, no oil or anything like that that's going to reduce the amount of friction available. So these tools only work under dry friction. So let's go ahead and take a look at our first example. And this example here is very similar to the one that we talked about before, where in this case, we have a rod, but it looks very similar to a ladder, and that rod is resting against a wall. And what we want to know is how much force do we need to apply down here at point B in order to prevent the rod from sliding down the wall and landing on the floor. So very similar to the ladder example that we talked about earlier. They tell us that the contact surface at point B is smooth. And what we mean by smooth is that right down here, there is no friction. Whereas the coefficient of static friction between the rod and the wall, so up here at point A, there is a friction force. So depending on the situation here, you may have like smooth surfaces. To me, the one we're most familiar with is like ice. If it gets icy out or if you're ice skating, we know that on ice, there's very, very little friction. That's the reason why we fall on ice so often. So you can kind of imagine this rod resting against a wall, but the bottom of the rod is resting on a surface like ice, okay, where there's very little friction involved. So let me go ahead and switch over to my iPad so we can analyze this situation. Okay, so what we're going to be doing here is we're going to be looking at this example, but we're going to actually look at it under a few different conditions because it's going to help us have a deeper understanding of how engineers can use statics as a support force. But just like we've done in every case, the very first thing that we need to do is we need to start with a free body diagram. So let's go ahead and take a look at that first. So for my free body diagram here, I am going to draw my rod AB. So point A at the top, point B here at the bottom. So I separate my rod from its surrounding environment. I don't care about the floor. I don't care about the wall. I just care about my rod. Second step after I've drawn a picture of my rod is to think about my reaction forces. So my reaction forces here are going to be a few of them. I'm going to have a normal force here at B, and I'm going to have a normal force here at A. And then I also have to think about the friction force. So one of the things about the friction force is that we have to think about friction opposing motion. So in this case here, when we think about opposing motion, we have to think about what direction does my rod want to move in this particular case. And they give us a clue when we read the problem statement, is it says, what's the minimum force P to prevent the rod AB from sliding? So we know if we were to remove P with that slippery surface on the floor, that my rod would want to slide down the wall. So at point A, I talk about the direction of impending motion. So impending motion here. I always like to draw that on my free body diagrams to help my brain help me with trying to understand the direction of my friction force. So at point A, the direction of impending motion is down because that's the direction that my rod wants to slide. And at point B, the direction of impending motion, I usually just label it IM for impending motion, is going to be to the left. So the thing about friction is friction always prevents motion. It always opposes motion under certain situations. So by identifying what the direction of impending motion is, we can automatically determine the direction of friction. So generally speaking, what we would have here for our support force is we would have our friction force at point A being upward, opposite to the direction of impending motion. And under most situations, the same thing would happen at B. We would have a force of friction at point B that is opposing motion. Now, one of the things you're going to say is, but wait a second, I thought you just said that surface B is smooth, and it absolutely is. So we can say right off the bat that that friction force there at point B is 0. We don't have to think about that one too hard. Okay, so we've got our normal forces at A and B. We took care of our friction forces at A and B. That ends up being all of our support forces. Now what we need to do is what forces are trying to cause motion. And for us in this case here, we're going to have the force of weight. So the weight of my rod trying to pull it straight down towards the earth. And the other force that I have is I have this force P here. So this force P is applied to the right. That's the thing that's preventing my rod from sliding down. So that's the other applied force that I have in my scenario here. Now, now that I have that information provided, I've separated my rod, I've drawn a picture of it, I have my reaction forces here, I have my applied forces here. The next thing I need to do are axes and angles. And for my axes and angles, what I'm going to do is I'm going to create my axes. I'm going to put those down here at point B. And the reason why I'm choosing point B in this particular case is because I want to eliminate the force P. When I get to my moment equation, I don't want to have to deal with that because it's going to help me find some other things instead. Okay, so I'm going to go ahead and do for point B in order to help me figure out what forces, or excuse me, what the moments are in that particular case. Then the other thing I have to contend with here is dimensions. Here I'm going to have to figure out the dimensions of various things. And so what I have for dimensions is down here, this guy here is 4 meters. And then over here, this one here is going to be my 3 meters. So I could even label this as my typical 3, 4, 5 slope triangle that we've seen many times over the course of this semester. Okay, so I've got separated my rod, drew a picture of it. I've got my reaction forces, my external forces. I've got my axes and angles available. And then I also recorded my dimensions for my moment arm. So the only thing that's really new when it comes to drawing a free body diagram involving friction is I have to think about the direction of my friction force. And in this case here, that means I need to know what's the direction of this impending motion. If my rod does start to slip, what direction is it going to start to slip? Okay, so with all of that in mind, I'm going to go ahead and talk a little bit about what my unknowns or my knowns are. So I've got more information in my problem statement that I need to account for. So it says determine the minimum force P to prevent the 30 kilogram rod. So I have to think kilograms. Kilograms are units of mass. So the mass of my rod is 30 kilograms. And I want to prevent that from sliding. The contact surface at B is smooth. The coefficient of static friction between the rod and the wall at point A is mu sub s at point A is equal to 0.2. So now that I'm on my iPad here, let's just go ahead and define this here. This guy here is called Greek letter mu, mu, okay? And that is the coefficient of friction. And if we talk about mu sub s, that's the coefficient of static friction. And we talked about it in the graph a few minutes ago. This equation using static friction is only applicable at stage 2, that breakaway point, right? This is the breakaway point. Up until the point where we reach that threshold between no motion and motion, we know that our friction force is equal to our applied force. And then at that peak, that's when we know that my friction force for, well, here, I usually label it F sub S, right, is equal to mu sub S times my normal force. So this is static friction at the breakaway. And that's equal to the coefficient times the normal force that's present. Okay, so that's at that condition. In this case, we're only analyzing static friction. We'll look at kinetic friction if you take EGR 207 in the future, but right now we're only dealing with static friction. So we're only interested in what's happening at that threshold between no motion and motion. All right, so let's go ahead and work on our, well, here, let's go ahead and define our unknowns. So our unknown in this case here is we're trying to figure out what is that force P. So then we can go on and look at our math and our equations that we're going to use. Now, for us, for our equations, we can still make use of the equilibrium equations because we want our rod to be in equilibrium. So we still have access to our equilibrium equations. And now we have this new added equation of what is the static friction force at this breakaway point where it's transitioning from no motion to motion in our graph. So we're going to go ahead and look at our equilibrium equations. The first one is to sum our forces in the x direction. Look at our free body diagram, and in the x direction, we have our force P acting to the right, so that's positive. We've got our normal force A at point A, and that's acting to the left, so that's negative, and that's it. That's all we've got in the x direction. So I have this force P acting to the right in the positive direction, and then I subtract away from that the normal force at point A. So there's my equilibrium equation for the forces in the x direction. Then in my y direction, revisit my free body diagram here, and in the y direction, I have this normal force here at B in the positive y. I've got the weight of my rod in the negative y, and then I also have my friction force at point A here that's acting in the positive y direction. So those are the three forces I need to contend with for the forces in the y direction. So the normal force at B minus the weight plus my friction force at point A, and all of those will equal 0. So they gave me mass. So this is one of those cases where we need to be able to convert between mass and weight. Mass was given to me, but I need weight because I'm doing the sum of the forces, and weight is a force, not mass. So weight is going to equal to mass times gravity. I am in the SI system, so I will take that mass, 30 kilograms, multiply that times 9.81, which is the acceleration due to gravity in the the SI or metric system. And then when I do that math, we'll come out with 294.3 newtons. So I can rewrite that equation there. The normal force at B minus my weight is 294.3 newtons plus the force of friction at point A. Okay, so I've got two unknowns there. I've only got one equation so far. Well, I've got two equations, I guess. I've got equation 1 up here when I sum the forces in the x, and then my second equation when I sum the forces in the y. My last equilibrium equation, I'm going to sum my moments about point B. That's where I chose my coordinate system to start. And up here, when I do that, I have got this force P and this normal force at B. These two both intersect by point B. So no forces mean no moment arms. So depending on your preference here, P, no moment arm means no moment. Normal force at B has no moment arm, so no moment. Come up here and I look at my weight. My weight here is going to be acting in the middle of my rod. So the moment arm for my weight here is going to be half of this dimension. So if the overall horizontal dimension is 4, my weight is going to act exactly in the middle there. I'm assuming that the density of my rod is uniform throughout. So the weight is going to be in the exact center of my. So I'm going to take my weight, multiply it by 2 meters, my moment arm, and then that's going to cause a clockwise rotation, which is negative. So my weight, we know, is 294.3 newtons. The moment arm is 2 meters, and we said it was clockwise, which is negative. The next thing that I have here is I have my friction force. My friction force over here at A is going to be a full 4 meters away from point B, and it's going to cause a counterclockwise or a positive moment. So my friction force at A times the 4 meters is positive. And then finally, the last one I've got here, I've got my normal force at A, that's multiplied by 3 meters, force in the X, moment arm in the Y, and that's going to also cause a counterclockwise. So the normal force times 3 meters, normal force at A times 3 meters, and that was causing a counterclockwise or a positive moment, and all of that adds up to 0. So let's go ahead and take stock for just a minute. I don't know P, that's one unknown. I don't know my normal force at A, that's 2 unknowns. I don't know my friction force at A, that's 3 unknowns. And then I also don't know my normal force at B, that ends up being 4 unknowns. Well, we've been talking all along the fact that we can only solve for as many unknowns as we have equations, and equilibrium alone only gives us 3 equations, sum the forces in the X, sum the forces in the Y, and sum the moments. I need a 4th equation, and where I get that 4th equation is this equation. Whoops, sorry, erasing when I mean to be pointing. There, we got my friction equation right here. That ends up being our fourth equation, and we haven't really talked about that one yet. So this is equation number 3. And then equation number 4 is going to be my coefficient of static friction. So my friction force at A is going to equal to mu sub S, that coefficient of static friction, times my normal force at A. Well, they told me that the coefficient of static friction was 0.2, and then my normal force at A. So that ends up being my fourth equation. So when I go through to solve this, what I'm going to do is I'm going to basically combine these last two equations. So if I take equation 3 and 4 and I combine them together, what I will end up with is I've got a negative 294.3 newtons times a moment arm of 2 meters, plus my friction force. This is where I want to do the substitution. I know my friction force is 0.2 times the normal force at A. And then I have to multiply that times my moment arm of 4 meters. And then add to that my normal force at A times my moment arm of 3 meters. And what ends up happening here is now I've eliminated one of my unknowns. I've got the normal force at A showing up in 2 different places. And now I can use my algebra skills, combine like terms, and then solve for the normal force at A. I'm going to go ahead and allow you to do that. Hopefully we've reinforced your algebra skills enough that that's something that's within your capabilities with confidence now. You should be able to find out that the normal force at point A is 154.89 newtons. Okay. Now that I have that normal force, now I can go back up and I can take a look at something. And what I see is my first equation, P is minus the normal force at A is equal to 0. So basically P is equal to whatever my normal force at A is. And I just found that. It's this guy. So now I'm going to use my first equation, equation 1. And in equation 1, it said that P minus my normal force is equal to 0. So P is equal to my normal force at A, which is equal to 154.89 newtons. Or if I want to round it to 3 significant digits, I got 155 newtons, and that is acting to the right. It comes out to be positive, which means my free body diagram is correct. So that means that drawing P to the right was the correct way to go. So right here, I have solved our problem. Okay, it wanted me to know what is the minimum force of P to keep the rod from sliding down. So if I apply 155 newtons to the right, I should be able to maintain equilibrium and my rod will not slide down. Awesome. Well, I can never be satisfied with that. What I want to do is I want to go ahead and play out a second scenario because I want you to understand how the directionality of the free body diagram and how we show friction equations, how that can change. So what we're going to do is we're going to do a second case here. So I'm going to go ahead and draw a line across my iPad because now we're doing a new scenario. And what I'm going to do is I'm going to come up here and I'm just going to copy my original free body diagram. See if I can do this decently here. So I want to copy my original free body diagram. And then I'm going to come down here and I'm going to display it again. So for you and your notes, you might want to go ahead and redraw this. And here's the thing is almost everything on my free body diagram is going to remain the same in this second scenario with 2 major differences. What I'm going to do in the second scenario here, go back up here, is I could imagine a possibility that if we start out with P equal to 0, because 0 is less than 155 newtons, my rod's going to slow down. I could increase P to 5 newtons, 10 newtons, 20 newtons, 100 newtons, 150 newtons. I can keep pushing P up, but until I get to that point of 155 newtons, my rod is going to slide down. But I could imagine if in my head, if I keep increasing P even more, that eventually my rod is going to start to move, but this time it's not sliding down the wall. It's going to start to move to the right at point B and up the wall at point A, right? And this is what we do with ladders a lot of times. We'll rest the ladder against the wall, and then we'll apply a horizontal force to try to get it to slide up the wall. Well, how much force does P need to be in order to have the rod not slide down, but to slide up? So that's what we're going to do in this second scenario. So if I come down here and I think about what impact does that have on my free body diagram? Well, I'm talking about changing the direction of impending motion. So I need to erase the direction of impending motion. And now we're going to say that impending motion is up the wall, and it is also to the right. So if that's the direction of impending motion, then the other thing that I need to do is I need to come down here and think about the direction of my friction. So in this case, if impending motion is up the wall, that means that my friction force is now located in the opposite direction. Now, my friction force at B, technically speaking, it would be to the left, but we still have a smooth surface, so we're still going to have no friction at point B because it is smooth. But if friction was present, we would know that it would be pointing opposite to the direction of impending motion, or to the right, or excuse me, to the left. Other than that, the only thing that changes in our analysis is going to be the sign of our friction force. So we got to go back up and take a look at this. Look at each of our four equations. We had P and we had our normal force at A. This equation doesn't change. When we summed our forces in the y direction, though, we had this friction force here. That's now going to equal to a negative friction force because we changed the direction. It's now pointing down instead of up. So we know that one was going to change. The other thing that ends up changing is when we take a look at our moment equation. Before, we said that the friction force caused a counterclockwise moment. We know counterclockwise is positive. So that is going to now be a negative value because we've reversed the direction. Instead of it causing a counterclockwise rotation, now it's going to cause a clockwise rotation. So we need to think about what impact does that have. So we come down here and we take a look at it, and the difference is that when we write our moments, sum our moments about point B, we're still going to have a negative 294.3 newtons from our weight in the 2 meters. But now we're going to have a minus 0.2 times the normal force at A times 4 meters. And again, this is because the friction force at A is down, not up. Okay, so that's why we made that change there. And then we're going to still have our normal force at A times 3 meters equal to 0. And what that means is now if we go in and again combine like terms and solve from N to A, I'm going to allow you to go ahead and do that on your own. What we should get from this equation now is our normal force at A is equal to 267.55 newtons. And we know that our force P is equal to that normal force. So that's going to equal 267.55 newtons. So that P is now equal to 268 newtons, and it's still going to be to the right. Okay. So if we say that this guy here was case 2, and this guy up here was case 1, what I want to do before we finish up this example is compare these two cases and see what we've learned about the overall motion of this rod. And the way I like to do this is to think about this in terms of thinking through the different cases. So what did we learn in case 1? Is that if P is equal to 150 newtons, that is less than the critical minimum P of P equals 159 newtons. So what that means is if P is equal to 150 newtons, in this case, the rod will slide down. P is not enough to prevent motion, so the rod is going to slide down and there's nothing we can do about it. At the point where P is equal to 155 newtons, that's equal to this critical case of P being 159 newtons. That was the result of case 1. And in this case here, the rod will be in equilibrium. Well, let's go ahead and think about this. What if P is equal to 200 newtons? That's greater than P of 155 newtons, but it is less than P equal to 268 newtons, right? So it's in the middle there. So if P is equal to 200 newtons, the rod will also be in equilibrium. Okay. If we let P equal to 260 newtons, again, it's greater than the minimum value. It's less than the maximum value. So in this case here, the rod will also be in equilibrium. Okay. But if we let P equal 300 newtons, 300 is now greater than our maximum value here. And in this case, the rod will slide up the wall. Okay, so that's what we're learning here from this scenario, is we talked about the fact that P has to be within a certain sweet spot. And in this case, anytime P is greater than or equal to 155 newtons, but less than or equal to 268 newtons, it will be in equilibrium. If it's less than 155, it's going to slide down. If it's greater than 268, it's going to slide up. But as an engineer who wants my system to be in equilibrium, I need to make sure that I guarantee that force P is somewhere in that sweet spot, somewhere between 155 and 268 newtons. As long as I stay in there, I should be just fine and I can maintain equilibrium. Okay, so I hope that example helps. I think it's a really useful one. Okay, so in this case here, we're going to take a look at another example, and I really like this one because it allows us to combine what we learned in Chapter 6 about machines and what we've learned all semester about equilibrium with this new stuff of what we're learning about in terms of static friction. So in this case here, we have what's called a block break. And all a block break is if you look down here at point B, it's a piece of what appears to be metal. It doesn't have to be metal. And it consists of a pin-connected lever right here and this little block here at point B. And what we know about this machine is that if I apply this force P upward to the handle, that's going to increase the normal force between B and this wheel here. Okay, so there's going to be more force applied, more normal force applied here. And we know that friction is related to normal force. So as P goes up, that normal force is going to go up, and the amount of static friction that can prevent motion is going to go up as well. They tell me that the coefficient of static friction between the wheel and the lever is 0.3. They also tell me that a torque of 5 Newton meters is applied to the wheel. So this wheel wants to rotate. It wants to rotate at 5 Newton meters. And what we want to do is we want to apply a force to this brake, this force P here, to make sure that it will not move. So we're going to take a look at a couple of different cases here. Is that if force P is 30 newtons, is that enough to keep it stationary? Or is a force P of 70 newtons needed in order to make sure that the wheel doesn't move? So we're going to go ahead and test out a couple of cases. So let me get my iPad set up so that we can do that. So first things first, I hope that this is obvious that this is not a truss, right? It doesn't have any triangles in it. There's no two force members or anything like that. So it's designed to move because I can change the amount of force on P and make that lever move up and down. So hopefully this one's pretty obvious that this is a machine. So we know from chapter 6, if we're analyzing a machine, what we have to do is we have to draw free body diagrams of each piece. So I'm going to go ahead and do that. I'm going to draw a free body diagram first of the wheel. So there's my wheel. And the free body diagram of my wheel, in terms of its reaction forces, what's preventing motion, I have right here a pin connected joint. So I'm going to have an OX and an OY. Pin joint prevents motion to the left and right. It also prevents motion up and down. It does allow the wheel to rotate, so there's no reaction moment there. And then in terms of other reaction forces, the things that are preventing motion, I know that there's a normal force here at point B. And then I know that the direction of impending motion is clockwise. I know that because I've got up here this 5 Newton meters. It wants to move clockwise. So that's the direction of impending motion. If I don't pay attention to that, my wheel will move. So I know from that that my reaction force here is going to be a friction force here at B, and it's going to be opposite to the direction of impending motion. And then the other thing that I have to contend with here is I have to think about my applied forces. And there aren't any applied forces as in like forces that cause translation. The only thing that's applied here is I do have that 5 Newton meter moment that's being applied, trying to rotate my wheel counterclockwise. So that's what I know in terms of what's going on with my free body diagram of the wheel. Now, before I go through and start to solve things, let's just go ahead and reinforce what we learned back in chapter 6. I'm going to go ahead and do a free body diagram of my my handbrake lever. And again, this challenges my limited abilities to draw. So there we go. And then from here, I know point A is over here. I know that this is point B. And in terms of reaction forces, what is preventing motion here? Over at point A, I have a pin joint, so I'm going to have an AX and an AY. Okay, so those are my reaction forces that are preventing motion. And then the other forces that I have here is I have that normal force and that friction force from point B. But the reason why I wanted to draw both of these right away is we got to remember what we learned about in the end of chapter 6 in the last video, is that if this normal force here is acting up, this normal force is the force the lever is applying to my wheel. Then I need to think about, well, what force is my wheel applying to my lever? That's going to be equal and opposite. So I'm going to have a normal force at point B acting down. This force here and this force here is an action-reaction pair. They have to be opposite, equal and opposite to each other, so when we add them up, they cancel each other out. Similar thing happens in terms of the friction force. If my friction force for the wheel is to the right, then I need to draw my friction force acting on the handbrake to the left. And again, just like the normal forces, these two here are an action-reaction pair. They have to cancel each other out. And then the only applied force that I have to my handle here is I have this force P acting up. Okay, so notice here that even though I've got this force P acting up, the P only shows when I look at the lever of my handbrake, right? P does not directly impact my wheel, so I can't analyze just the wheel because I don't have enough information. I don't even have the force P that I'm taking a look at here. So what I'm going to do next is I'm going to go ahead and take a look at the wheel first. So let me go ahead and just label this. This is the wheel and this is the lever. So if I look at my wheel, I'm going to analyze it first. And before I actually start writing the equations, we need to go back up and take a look at a couple things because I'm noticing that I'm still missing some key pieces of information. So when I look at my problem statement here, what do I know about my problem statement? It says the block brake consists of a pin-connected lever and a friction block at B. The coefficient of static friction between the wheel and the lever, that's mu sub s, is 0.3. And then I know that my moment that's being applied is 5 newtons times meters. And I want to know what if the brake will hold if P is equal to 30. Okay, so case A is P is equal to 30 newtons and case B is P is equal to 70 newtons, and we want to know what's going on with that there. The other thing that I'm thinking about as I'm getting ready to do this is I did forget to put my axes and angles down. I forgot my dimensions. I got so excited about talking about action reaction stuff, I didn't finish up my free body diagrams. So good reminder to myself to make sure that I'm paying attention to that stuff before I move forward. So I separated the wheel, I drew a picture of it, I got my reaction forces, OX, OY, my normal force, my friction force. I have my applied force, 5 Newton meters, but I didn't put down my axes. Oops, bad me. Okay, and then I also didn't put down my dimensions. And in this case here, the dimension I'm most interested in is I need to know what is the radius of my wheel. And they gave me that the radius here is 150 millimeters. Okay, and running out of room here, that's going to be 0.15 meters. I like to go ahead and convert those to meters. So I move it to 3 decimal places to the left. That's 0.15 meters for when I get to my moment equation. And then to go ahead and finish off my free body diagram for the lever. Again, I didn't think about my axes and angles. I'm going to use point A. Go ahead and eliminate AX and AY from my moment equation. And then I forgot to put down my dimensions. So I know that this guy here is going to be 50 millimeters, which is 0.05 meters. I know the dimension between A and B here is 200 millimeters, or 0.2 meters. And then between B and where force P is applied, this is 400 millimeters, which is 0.4 meters. Okay, feel better about my free body diagrams now. So I took another look at my problem statement. I revisited my free body diagrams, made sure that those were all good. So now I can go ahead and analyze my wheel. So analyzing my wheel, if I sum my forces in the X direction, I have OX plus my friction force. If I sum my forces in the Y direction, I have OY plus my normal force. And if I sum my forces, or excuse me, sum my moments about point O, OX and OY, they both intersect point O, so no moment. So OX, no moment arm, no moment. OY, no moment arm, no moment. My normal force at B, slide it, principle of transmissibility, it also intersects point O. Sorry, I got a little ahead of myself there and then didn't complete my thought. So normal force at B has no moment arm, so no moment. I do have my friction force here. My friction force is going to cause a counterclockwise positive moment, and it is 0.15 meters away from point O. So I got plus my friction force at B times 0.15 meters. And then be careful here. Some students are going to be, oh, well, I'm all done, so I don't have any friction. You got to remember, what's the thing that's making it move? We've got this guy here. You got the 5 Newton meters acting clockwise. That is a negative moment. Okay, and then I add all of those up, and that's equal to 0. So what that means is I have my friction force at B times the 0.15 meters minus 5 newtons times meters is equal to 0. If I solve for my friction force at B, I should get 33.333 repeating newtons. So what this represents to me is this is how much friction is necessary to maintain equilibrium. Okay, so let's go ahead and just write that down. How much friction to maintain equilibrium. Okay. Now, if we say that, we also know that my friction force at B is equal to mu sub S times my normal force at B. Well, if this friction force is 33.333 newtons. And that's equal to mu sub s, which was 0.3, right? That's what they gave us in the problem statement, was 0.3, times my normal force at B. That tells me my normal force at B is equal to 111.1 newtons. So if I don't want my wheel to move, I have to provide at least 33.333 newtons and 111 newtons of normal force in order to prevent that motion. And where that's helpful to me is now I can come back and I can retake another look at my lever free body diagram. What I just found was N sub B and my friction force at B. So I think what I'm going to do here to help us move this along is I'm going to go ahead and copy my free body diagram. Let's copy this guy and move it down so we can take another look at it. I'm going to even just blow it up a little bit, make it a little bit bigger for us to take a look at. So what we just found is that we know this guy is 111.1 newtons. We know that this guy here is 33.33 repeating newtons. Okay, so that's why we analyzed the wheel, is it helped us find the normal force at B and the friction force at B based on how much torque or moment is applied to my wheel. So now that I have that, I can analyze my lever. So my forces in the X, I've got AX minus my friction force at B. So that's going to just basically tell me my AX is also 33.333 repeating. Not really useful for what I'm trying to find, but I've accounted for it. Sum my forces in the Y direction. I have AY minus my normal force at B, which is 111.1 newtons, plus my force at P, and set those equal to 0. Can't solve that right now, so set that to equal to equation 1. And then my last equation here, I'm going to sum my moments about point A. AX has no moment arm, so it's 0 moment. AY has no moment arm, so it's a 0 moment. My normal force at B is 111.1 newtons. It is a total of 0.2 meters to the right. It's going to cause a clockwise or negative moment. My friction force at B, slide this guy over, and what you should see is that moment arm is the 0.05 here. We know my friction force is 33.333 repeating times the 0.05 meters. And that's causing a clockwise moment, so it is also negative. And then we've got my force P. So this guy here is going to cause a counterclockwise moment, and it's a total of 0.6 meters. I've got to add these two numbers, 0.6 meters here. Okay, so P times 0.6 meters, and that's causing a counterclockwise or a positive moment. So look at this. In my equation, the only thing I don't know is P. So now I can use my algebra skills and find P, and what you should find is P should be 39.8 newtons. Okay, so that's our test case. If P is at least 39.8 newtons, then I should be able to maintain equilibrium, and my handbrake will be enough to prevent my wheel from slipping. If P is less than that, we got problems. It's going to slip. If P is more than that, well, in this particular case, it's just going to provide that much more of a force to prevent that kind of motion. So with all of that done, now we can go back to our original problem statement and say, what were we trying to do? The two cases we wanted to look at was P equal to 30 and P equal to 70. So now we can finally come down here and draw some conclusions. For case A, P is equal to 30 newtons. That is less than 39.8 newtons. So that means that no equilibrium. The wheel will move. Okay. And then for case B, when P is equal to 70 newtons, that is greater than the 39.8 Newton minimum. So yes, we have equilibrium. So the wheel will not move in this case. Okay, so that's what we end up learning about there. So it ends up being a really important thing here is we have to remember that friction's different from all of the other ones. There are test cases. The only thing we can do with that static friction equation is remind ourselves that that's only valid at one point in time when we're on that threshold between no motion and motion. We're on that teetering edge, that peak of our friction graph. If it's less than that, no motion. If it's more than that, we got motion. That's when that equation applies. But as we've seen in the case of the rod that we looked at in the previous example, and now here with this handbrake, is that we can use that equation to try to help us understand, is my design in static equilibrium for a particular circumstance, or am I at risk of having it move? And engineers use those test cases all the time to make sure that we are going to have no motion when we need to maintain equilibrium. Okay. So there we go. Those are our two examples of friction. Believe it or not, that means that we are done with this unit. I told you it was going to go by real fast, especially with my absences for my health issues interfering there with a little bit of stuff. But coming up soon is going to be the chapter 6, and through today, the introduction to friction. Those will be coming up when the next assessment. So students in my face-to-face class. When I get back from this conference, we're going to talk about the assessment and the timing of it. I have a proposal, but I want to wait and talk to you about that proposal to see how things go for you with this online learning. So when we get together, it'll be Monday, November 10th, I think is the correct date. We'll talk about how things are going, and I've got a couple of ideas on what to do about the assessment. But bottom line is that the chapter 6.1 through 8.2 assessment, it's going to run exactly the same as all of the other ones. You're going to have support available in Eagle. It'll be covering 8 learning objectives. You'll have 16 questions split between conceptual and problem solving. I'll give you the answer key after I get all the submissions in. Your score will be determined using a rubric. You'll have opportunities to fix mistakes, learn from your mistakes if you're not satisfied with the results, and we'll do a final Q&A before the assessment actually comes up. Format for the assessment is going to be exactly the same for all of that. So it'll just be the content and the learning objectives we're assessing that are going to be different. So with that information, those resources are already posted in Eagle. In summary here, we'll just kind of go back and review what we learned about friction, the fact that friction can either prevent motion. In this case here, this is when we're in equilibrium, where the friction force and the applied force are equal and opposite. My friction equation, Fs, is equal to the coefficient of static friction times the normal force, only applies right here at the peak. And then if you go beyond that, then you're going to get motion, and we're going to be in the case of kinetic friction here. So kinetic friction occurs when the body is moving. So obviously you're going to have some homework out there. You've got a conceptual quiz. You've got some problems to practice with here. How do we represent this idea of static friction to provide support for systems in equilibrium? So I hope this video helps. Please reach out if you need support. Otherwise, good luck.